So far, I've shown you several different ways of coming up with the probability of getting a certain number of successes out of a certain number of trials, given a certain probability of success on each trial. That is, if you have numbers for n and p and x, how to get the probability. Either using that formula, or a graphing calculator, or the table, or Desmos, or Excel, or something like that. You don't have to know all of those, but you have to know at least one or two. So from here on out, I'll assume that we know how to come up with the probability if we have numbers for n and p and x, and we'll recognize how to read a problem and interpret what it is it's actually asking so we know what we're dealing with for the n and the p and the x. So, some more examples. A multiple choice test has 10 questions, each with 5 possible answers. So you could answer A, B, C, D, or E. And that means if you're just guessing at random, you have no clue what the correct answer is, so you just pick either A or B or C or D or E totally at random, then you would have a 1/5 probability, 1 out of 5, which is 0.20, of guessing the correct answer. So on each question, you've got a 0.2 probability of getting that question right purely by guessing. What's the probability of getting exactly 1 out of 10 right? Notice this is a binomial probability situation where n is 10. That's how many questions there are. That's how many questions you could get right. P is 0.2. So that's for each of those 10 questions, that's the probability of getting that question right. And the x in this question is 1. You want to know what's the probability that the number of questions you actually do get right turns out to be 1. So now that we have our numbers for n and p and x, we can come up with the answer to the question. We can look on the table. I would go to the part of the table where n is 10, and I would look in the column where p is 0.2, and I would find where x is 1, and the probability that shows up on the table is 0.268. So that's the answer to that question. What's the probability of getting 2 out of 10? So same n, same p, but this time the x would be 2. So the probability, the answer to that question would be 0.302. What's the probability of getting 10 out of 10 right? What's the probability that you get a perfect score, all 10 right, completely by guessing? N is still 10, p is still 0.2, x is 10, and on the table, there's just a blank spot there. So the probability is practically 0. It's not really exactly 0. It's some really, really tiny number. But it's so small that if you just give it to 3 places after the decimal point, it's 0.000. What's the probability of getting 0 out of 10 right? That would mean you're getting all of them wrong. So that's where x is 0, and the probability there would be 0.107. Now, what's the probability of getting at least one question right? Ooh, you know what? That's something we've talked about before. Getting at least one right is the complement of getting none of them right, getting all 10 of them wrong. So it's got to be one or the other. If you get all 10 wrong, that means you did not get at least one right. If you got at least one right, that means you did not get none of them right. So the probability of getting at least one correct is 1 minus the probability that that's not what happened. You got none of them correct. So that would be 1 minus 0.107, which would be 0.893. Now, I should maybe mention that it would also be possible to answer this question about getting at least one right by saying, well, at least one means that the number of questions you get right is either 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. So you could add together all of those probabilities for all of those x's that are at least 1 and get it that way. That would give you basically the same thing. Might not be exactly the same because these down here aren't exactly 0. You might get a little round off error, but it would be pretty close. So you can add up the probabilities for all the x's that are at least 1, or you can just say, well, getting at least 1 is not getting 0. So 1 minus the probability of getting 0 right would be the probability of getting at least 1 right. Okay, next example. 5% of all widgets made are defective. So for any individual widget, it's got a 5% chance of being one of the defective ones. In a batch of 20 widgets, what's the probability that none of them are defective? So this is a binomial probability question. Can you tell what numbers we're using for n and p and x? N is the number of trials, so that would be 20. 20 widgets. Each one of those widgets might or might not be defective. P is the probability of being defective for each one of those 20 widgets, and that would be 5%, and as a decimal that would be 0.05. Careful, it's not 0.5, it's 0.05. To convert from a percent to a decimal, you move the decimal point 2 places. And the x in this question, how many out of the 20 are we talking about being defective? Well, none of them, 0 of them. So x would be 0. So in a situation where n is 20 and p is 0.05 and x is 0, what's the answer? Well, according to the table, that would be 0.358. Okay, what's the probability that exactly 1 is defective? So same n, same p, but this time x is 1, so the probability would be 0.377. What's the probability that exactly 2 of them are defective? Can you see it on the table? 0.189. What's the probability that at least 2 are defective? So there we got to add together all the probabilities for all the x's that are at least 2. That would be the 2, the 3, the 4, and so on. So we add up 0.189 plus 0.060 plus 0.013 plus 0.002 plus a bunch of zeros, and we get 0.264. And in case you're wondering, yes, we could also do it by taking 1 and then subtracting off the ones that aren't included, the probabilities for 0 and for 1. And if you were using that Desmos app, we could do it by giving it 20 for n, 0.05 for p, and then saying x is a minimum of 2 and a maximum of 20. So under functions, distributions, binomial distribution, the number of trials is 20. The success probability is 0.05. And where it says find cumulative probability, give it a minimum of 2 and a maximum of 20. And there it is, 0.264 something. Now, the other thing we're going to talk about in relation to binomial probability and binomial distributions is the mean, the variance, and the standard deviation for a binomial distribution. And there are simple formulas for all of those. The mean for a binomial distribution is n times p. The variance is n times p times q. And remember, q is 1 minus whatever p is. And the standard deviation is the square root of the variance. So the square root of n times p times q. So for example, If you go back to my silly broccoli example about inviting 4 friends over, and then the number of friends who actually like broccoli could be anywhere from 0 to 4. And this is what the probability distribution looks like. And we've learned how to take any probability distribution and calculate the mean by taking each number times the probability that goes with it and adding those together. So if we did that here, the mean would be 0 times 0.0256 plus 1 times 0.1536 and so on. And that would come out to be 2.4. But because this is a binomial distribution, there's a shortcut. For a binomial distribution, the mean is just n times p. So here that would just be 4 times 0.60, which is 2.4. And then for the variance and the standard deviation, we could do those the way we talked about in section 5.2, or since this is a binomial distribution, we can use the shortcut formulas. The variance would be n times p times q, so 4 times 0.60 times, and then q is 1 minus 0.60, which is 0.40. Multiply that out, you get 0.96. And the standard deviation then would be the square root of that number. The square root of 0.96 is approximately 0.98. So, example, given, and this is a multi-part example, all based on a situation where p is 0.25 and n is 18. So, first question, find the probability of x equals 5 successes. So if I turn to table B, look to where n is 18 and find where p is 0.25, and I don't see that on the table. There is no column for 0.25, so that's one problem with the table. It doesn't always work because sometimes you might get a p or an n that isn't one of the ones on the table. So in that case, we would have to use one of those other methods, like a graphing calculator or the formula or something like that. If we go back to the formula and put in 18 for n and 0.25 for p, and that would mean that q would be 1 minus 0.25, which would be 0.75, and x is 5, so that goes here and here, and then n would be 18, x would be 5, so 18 minus 5 would be 13 here. You calculate this out, it comes out to about 0.199. Or you could do this with a graphing calculator function, binom PDF on a graphing calculator, or on Excel, or on Desmos, or something like that. But the answer does come out to be 0.199. Okay, second question, what is the mean number of successes? So the mean is n times p. So here that would be 18 times 0.25, which is 4.5. What about the variance? The variance would be n times p times q. So here that would be 18 times 0.25 times 0.75, which comes out to be 3.375. And remember how we got q? Q was 1 minus p, so 1 minus 0.25 is 0.75. And the standard deviation is the square root of n times p times q. So it's the square root of the number we got for the variance. And that's 1.837, blah, 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 so about 1.8. Now, my last example in this section is shown here, and I'm going to come back in one more part of this video and give you the answers. But before I give you the answers, you might want to try and figure them out yourself. So at this point, this is just a review example. I'm not showing you anything new here. We're just reviewing the things we talked about in this section. So you should know how to do these. So try working these for yourself before you play the video where I show you what the answers are.